Okay. So with CCNA2, routing and switching essential, we're going to go deeper into both routers and switches. And we start off with routing concepts. Now, in a way, this module, the chapter 1, is a really good chapter for consolidating your knowledge of routers, and it will hopefully help plug some gaps in your understanding of what they can do. There's always a few packet traces to go with this chapter. I've got 4 here. I've got produced, and there's also a lab there, which is a really long document. Actually, it's like maybe 15 pages or something. And that lab is something I would encourage you to do, but it's possibly best done not in a class. It's quite a long lab, but it's a really good lab, and I'll tell you when that's coming up. So let's get started. You guys take your break, just timing it right. So if I just run this through and try and get this done before the break. What time is he open till, the guy in the cafe? 8 o'clock?
I think so.
Let's try and aim to get this done in an hour, right? So at least 7:45, that'll be good. And then we can get time for some practical work after that. So let's begin. So generally speaking, we're going to talk about the configuration of routers. That includes the functions, settings, connectivity of networks, decisions routers make, so how they forward packets, and also the way that encapsulation and de-encapsulation is used when you're switching packets between interfaces. Also something called the path determination function. So which path should a router take? How is that elected? Router operation, so how does the router learn about other networks in a small to medium sized business network? And how the routing table is built up, various different, well, there's different protocols with routers, but we'll look at both static routes and also the the dynamic routes, directly connected routes as well. Starting off with the configuration of a router, let's just start with really why routers exist. So we know that networks are relied on for these various applications. IP telephony, video, gaming is obviously a very popular one too, actually, with networks, and obviously e-commerce. And some of the characteristics when we discuss networks relate to topology, which is a bit like a work, like in a way, like a design. There's a physical topology, which is how you physically arrange cables, the devices involved, and how they're physically linked to each other, yeah, with the wires and the devices. Then there's logical topology, which is the path of data transfer. And this is sometimes different to physical topology. You might have physically cables going all over the place to these different devices, but logically it might be very tidy, yeah, in terms of how data is being moved around. Then we have speed, and speed is a measure of the data rate in bits per second of a given link in the network. BS, B/S there.
Is that bit per second?
Indeed. Obviously it's huger than that, isn't it? It's just the lowest level of it.
Yeah.
And these other bits and pieces, and all these things around here, we've mentioned 2 of the terms, but we've got here, other than topology and speed, we've got cost, security, availability, scalability, reliability. So cost is our expense of the component, but also maintaining a network and installing it. Security is a protection of that information and transmission. Availability is the uptime and the likelihood of that uptime. Scalability, can we increase the size of a network and decrease it as users change or data transmission requirements change. Reliability, this is the dependability of the devices involved. Downtime, how much time is there between faults, and there's an actual acronym called MTBF, which is the mean average, the average time between failures, how often they can occur on average. Why routing? Okay, so what is the function of a router? If this is ever defined, the router's job is to connect one network to another network. It determines the best route to the destination before forwarding traffic to the next router along the path. It's responsible for the actual routing of the traffic between the network, and it uses a routing table to determine the most efficient path using various algorithms and mathematical calculations that the CPU does of a router to work out the best way to get to a destination quickest way to get there. Little picture here. This is a WAN in the middle, and you've got a few different local networks, central branch and home office. This is like a bank, you can say. So a bank has a central city branch, national, and then you've got the kind of like a local branch there, and then there's also a home office. So how does that all work together? Say someone's working for a bank and they're working at home. They're linking into the branch. They can link to the central office, and via these routers, which is really what create this connection between networks, and obviously the internet between this, as in the cloud, it enables the connection to all these devices via this point, that point, and this point. Now, a router is a computer, so the physical machine. Computers themselves always have some basic things, right? So if you took a PC apart, you would find some of the same stuff in a router. You have got a CPU, which is like the brain, central processing unit. You've got an operating system, which is like what carries the kind of day-to-day operations. Like, the PC uses Windows, Cisco uses iOS. You then have to store in memory things, both in short-term and long-term. So we have this different types of memory and storage because of that. We have RAM, ROM, NVRAM, flash, and hard drive. So this idea of having volatile and non-volatile memory, non-volatile means that if the power's turned off, it stays. Yeah? And volatile, if power's off, it loses. You've got it, it's flushed, right? So the question asks, which one requires constant power to retain content? The power, in a way that the power on the NVRAM is always a certain charge of power going through the NVRAM to keep that content alive. So it's the former. Now also routers have specialized ports and interface cards. You can actually, you can get a router and you can change it. You can, like a PC, take off the bits and pieces in the back, the case, and slot things in. And sometimes in your labs, you'll be asked to do things like slot in something called an eWIC card or a extension card via the physical packet tracer interface and simulate with that. So keep that in mind too. The types of memory are explained in more detail here. So if you want to look at the slide, Haida, what slide number is that you got there? Tell me the number you're on.
This is 1113.
So in your materials, folks, the picture I'm looking at is a 1114, I think, or 1112. So the next or last? Probably you're on the one before me, I think.
No, it's 1113, but there's 3 pictures here.
Gotcha. Yeah, thank you. Good. In this table I'm looking at now, I'm looking for where that table is.
Yeah.
Somewhere in that list. 1113, I think it is.
Yeah,
so you can find it on your screen if you can't see that. It's tiny, right.
Computers.
Great. Tiny. Right might be tiny on the screen there. So if you see it on your own machine, please just zoom that up. Okay, so memory, we've got random access memory at the top. Volatile, temporary storage, runs the iOS running config, IP routes, ARP tables, and packet buffer. The ROM, non-volatile, permanent storage for boot, diagnostics, and limited iOS. So if, for example, the full iOS can't run, there's like a backup micro iOS on the ROM, which will give a limited functionality. NVRAM itself contains that startup config file. That's where it's permanently stored. Flash gives you non-volatile memory for permanent storage for iOS, other system-related files. Here's a physical diagram of a router here. Got some double slots to add the eWICs in. Flash card slots for storage, 2 4 gigs there. Another eWIC port there. Auxiliary ports, console port, USB port, LAN interfaces there, and a console USB, mini USB in. Console in via both that or that. The serial console, is disappearing. But you have the RJ45 here, yeah, which is the standard phone line in serial there. Okay, so routers interconnect networks. That's their job, and it forwards packets from place to place. The interfaces of routers, they connect both LANs and WANs, and a WAN is a wide area network, such as to an ISP, is like that kind of connection, a WAN connection. So it says a question, when a packet arrives on a router's interface, that router might be the final destination, so it might end here, or it might need to send it somewhere else. So it might need to go from here to there and then to there. Yeah? So router might be the end point, or it might be a forwarding point. How does it choose which paths to go on? So as an example of command show IP route, the sort of things that appear, and some of the features, some of the details are coming up below it. So what router is doing is, I mean, just the functionality of it, as it's working out the best path and forwarding it on. So what it does is, when it gets a packet, it examines the address it's going to. A packet contains both a destination address and source address. So what it does, it examines that destination address more carefully, and it uses the routing table to look for the best path to the network. That's how it's really doing this. It's just saying, right, okay, your IP address destination is, you know, it wants to go to 192.168.3. So it's just going to see which connections has it got, which networks is it connected to, and therefore, based upon that, it will choose. So it uses a matching system, and if a match is found, the router then encapsulates the packet into a data link frame of the outgoing exit interface and forwards the packet out of the interface to its destination. So as the exit interface moves on, the router can handle different data link layer frame encapsulations. It also might receive a frame from its Ethernet interface. So in that situation, it has to de-encapsulate the packet to search the table from matching network. Okay, so this match, once it's found, it will basically think about the idea of encapsulation. It puts a packet around it, really, around this thing. It puts it inside the corresponding frame for the right interface, so it goes out the right path. Now the actual way that it's called forwarding, the mechanism for moving stuff on. So there are different types of forwarding mechanisms, and there are 3 different mechanisms you need to understand. So just understand the difference between these 3. One is called process switching. So slower and older version of packet forwarding. Packet arrives in, it's forwarded to the control plane. So the CPU, like the brain of this router, matches this destination address with an entry on the routing table to work out which interface do I go out from. And it does it one packet at a time. So this is every packet in the stream is sort of one at a time. It just handles that. So it's quite slow. Fast switching. So what this does is this uses a cache. Now you know this idea of a cache on any machine is like a sort of a buffer storage, where it puts stuff in it temporarily, like your browser has a cache. And this cache is storing the next hop information. So what happens is a packet is forwarded to the interface. Again, it goes to the control plane. And the CPU now, rather than matching it in the routing table, it instead does a search for a match in the cache instead. So the cache might store commonly referred to addresses, say like over a year, it's picked up loads of stuff, right? So it just uses the cache. It's much faster to use a cache than go straight to a routing table. If there's no match and it can't find anything, it then goes back to process switching. Then it goes to a routing table, and forwarded on in the old way. That's it. This is much quicker because of the cache. It gives a quick lookup, so therefore it's just faster than process. But obviously it takes time to build up a good routing table. Okay, finally, CEF, Cisco Express Forwarding, fastest, most recent and preferred forwarding mechanism. So what this does is this builds something called, we were to talk about the cache earlier, this builds something a bit like the cache, but it's called an FIB, Forwarding Information Base, and an adjacency table. So what this does, this is much more responsive. Like the routing table, the cache learns stuff over time, right? Well, what this does is it automatically learns when something changes. So if the network changes and the adjacency changes, so other things have changed on the network and routers have done various updates and triggers, this changes the FIB, adjacency table, and it stores that information there. Okay, and this is usually best done when you have network convergence, when all the network is converged on all different ports and places. And so this is a faster even than the one before it. because of this adjacency table, is up to date. Doesn't need to learn anything, already knows what's going on. It also contains pre-computed reverse lookups, so it can go backwards and forwards. Next hop information for routes, interface and layer 2 information. Bit of terminology now, so you just say control plane is the word for the CPU area. Data plane is where the table is stored, an FIB. And we have this word ingress for incoming packets, and egress is the exit. So this ingress is coming in, and egress is going out. Incoming and exit. So one particular packet tracer activity here is called use trace route to discover network. This packet tracer activity, what you do is basically you run through it and you basically learn about the network via various commands. It's how you can learn about a network and what's on it by exploring it using trace route. There's also a lab that goes with it, which is done on a normal PC, and this is called mapping the internet. This is a good thing to do on a home machine, where you can look around and see how that particular that device is set up and what networks are on it. Okay, on to connect to a network. So home office is example given here. It's this one at the top. Laptops and tablets, network printer, using an Ethernet cable to the switch on the home switch port on the home router there. And the home router also connects the ISP using Ethernet 2, so here's your kind of internet connection. And the cable modem connects to the ISP network. There you go, there's the ISP there. It's your simple home internet connection there and what's going on with that. Now, working with a branch instead, so we did the branch office. So this is like a mixture of PCs, VoIP phones, corporate resources, file and printer servers. Connect to a switch, so you've got a switch here, all Ethernet. Laptops and smartphones connect to a WAP, which is so you've got wireless access point connected to the switch, and there you've got your tablets and your wireless devices connecting to it. The layer 2 switch connects to an internet interface on the edge router using Ethernet cable. So this device here, terminology, we call that an edge router. Okay, it's one that's right on the edge of the whole interface in this space here. Yeah. And this edge router connects to a WAN service provider. So this here, this red line is that WAN connection. Also it connects to the central office too. Central device, if you look over this lot over here, these bits and pieces. So similar in a way to the branch office, but what we also have is layer 2 switches, these ones here, connect redundantly to multi-layer 3 switches using Ethernet fiber optic cables. So what we have here is we also have a layer 3 connection, and in CCNA2 we look at that much more. This is to do with having a fail-safe, right, reliability, backup really for any device. That's why this corporate situation requires these things. Layer 3 multi-layer switch connects an Ethernet interface on the edge router using Ethernet. So you see here is the edge. The EI is here. And the corporate website server connects to this edge router interface. So see over here, this web server is running the website. It's actually the business is running it in-house. Yeah, and they can do that with an IP address, but this router is making that possible. Because this router is sent to the internet, right? Therefore, that's got an IP address which is public. And that means that public IP address can be picked up by this home office machine and accessed. It could be like a extranet or that kind of server, one of those virtual office environments. The edge router also connects to a WAN service provider and to an ISP for backup purposes. This router here is doing backups, yeah, or backup to here as an alternative, but also a WAN service provider too, which is via the cloud. All right, there's a structure there. So now on to default gateways, getting the pieces to the correct network. It says here. So let's look at this packet as an example. Destination MAC address, source MAC address, source IP, destination IP address. It wants to get to 172.161.99 with some data. 172.161.99 is the server over here. This device is coming from here, and it will always need a default gateway if it's going to have to get something beyond the network. Okay, so here we've got these routers, and it's indicated here that this is the default gateway for this local area network. Therefore, that PC has to be configured with the default gateway address of that point in order for it to come out onto the network to get this web server. Same for this device too.
This device doesn't need the default gateway, does it?
Say again?
Does it need default gateway?
Yeah, both do, yeah. If it wants to do stuff beyond here, then yeah.
Oh yeah, if they want to pass, yeah.
Yeah. Any device we will attach to the switch will need that default gateway now.
Okay.
Anything we put onto this that wants to get beyond it. Even for internet access, or this is a web server particularly. Yeah? Okay. Now, the basics you need, obviously, IP address, subnet, mask, and default gateway. So this thing here, it's saying here, when a host sends a packet to a device on the same network, say this wants to go to here.
That's what I mean.
Yeah.
They don't need it.
No, no, you're right. Yeah, that's sure. Root doesn't get involved with this.
Yeah,
This is a local network, so
Exactly.
these two can talk to each other regardless. Don't need default gateway. Yeah, that's fine. When it goes beyond, it's because the IP address is like 1.110 and 1.111. They're on the same network.
Same network, okay, but
Same
they want to
network,
pass to another network.
Yeah, then
Then
this one here is 172.16.1. This is 192.168. One
Yeah.
dot. Yeah, different network over here, definitely. So then we have to have default gateway. Okay. Right, that's good. Document network addressing. Now, they always, when you have documentation for networks, this is what you should have on the documentation. Device names, interface used in design, IP address and subnet masks, default gateway addresses. Yeah. So there's two useful documents you see here. One is the diagram, topology. That's a topology diagram there. Packet Tracer makes wonderful topology diagrams. That's what you should do to make it. And an addressing table captures your device names. This is really useful too. You see this on your Cisco labs. Sometimes at the top you get this stuff here: device, interface, IP, subnet mask, default gateway. Really useful stuff for anyone working on a network, in a team and so on. Yeah, it's all there. Okay, this is the easy bit. So how do you enable IP address on a host? Two ways: statically, you manual configure the IP, subnet, default gateway, and possibly the DNS server IP address. Servers and printers often don't change, so they often get a static address because they're not changing much. They're always turned on. Dynamically, other way of doing it, you turn on your dynamic DHCP. So you tick the top one here. That gives you automatic IP allocation. And then the server will give you the IP address, subnet mask, default gateway, and the DNS information. Yeah, most hosts nowadays use DHCP. Just checking, folks, remind myself, chapter 10 or 11, CCNA2, DHCP. We talked about it somewhere. It was somewhere in there, yeah. All right. Device LEDs, okay, these are the lights. What these lights mean? These lights just show different things. The lights are here, and there's two here, S and L. So just so you know what these lights mean, the S and L lights, S is speed, L is link. Depending on how fast this is flashing is how fast the speed is, and L link is active or inactive. That's very standard for Ethernet. The green flash is like an active port. Console, this is number 2 here, just says active if it's green, and off is not inactive. Same for the USB, which is number 3, that port there, active or inactive. Okay, no light means there's possibly a problem there. Amber light on a Cisco 2960 switch is a malfunction. Okay. Console access. Here's the ways we can now talk to a router. Various things. We got the serial port, the old-fashioned, and we have this on the back of your PCs here in the college. These have this light blue cable you've seen. That goes straight to a console port under the ground into an Ethernet point. Yeah. And the software we can use for that serial connection is Teratom or PuTTY, as long as you set serial when you can make your connection. The other more modern approach is the USB Type A port. And here you can buy either, you can use a console cable again for that. Obviously it's got USB on one side of it. But this goes from USB on your PC. You know, like we don't have serial ports on machines really nowadays. So but you have a USB port, right? Type A. And that will, using a cable, Type A to a Type B converter to make that connection to that connection. Okay, that's that line there. That'll allow you to connect to more routers using a more modern connection. That's more likely to be the case where you do it. If you get stuck, you also can get a USB to RS232 serial port adapter, which means you can make USB and RS232, like this is the RS232 here, talk to each other. So you can have a USB interface instead on that. Yeah. That's if you've got a console cable and want to connect USB to a console cable. So you get a USB port, you buy this USB to RS232 adapter, plug that into there, whoops, and that side of it goes onto this, and then you can console in. Again, those two softwares are needed. Okay, onto the switch management interfaces now, connecting devices. So network devices require IP addresses so we can have connections from Telnet, SSH, or even HTTP. A switch requires an IP address to be configured on a virtual interface. We call this the SVI. The commands in the left are an example of a configuration of a SVI on VLAN 1. So you see here, command interface VLAN 1, IP address given 10.2. Yeah, and subnet mask, no shut. This is all done on S1. So here we're configuring that switch, that particular interface, VLAN 1, giving it an IP address. Okay. We also need to make sure that a switch has a configuration to default gateway. So when I exit this, I'm going to give it an IP default gateway of 10.1. That takes me right there, that point there. Okay, that's my default gateway exit. Packet tracer documenting the network. I'm going to just distribute. Let's see what I've got. Order I've got it in. Yeah, documenting. Now this particular packet tracer just helps you document a network. This isn't something you just complete. And I'll let you choose which ones you want to do. Let me hand these ones out now. I'm still going to go over the presentation. Let me dish these out now so you can at least look at this. Okay, Astra, can you let me pass these out? Yeah. Pass them down. 1, 2. Just one each, yeah. One batch each. 2. Everyone got one? You have one. You don't have one. There you go. Right, good. Okay, done. That's called documenting. Here's a little scan of what this is involving. Your job is simply to document an address scheme and connections using the central portion of a network. So you use a variety of commands to show parts of the network, and then you fill out this table completely. And then you get the right values in there, and you're all good. Okay, so that's really a useful thing to do. This is documentation. Put that aside. This is what number is that? 2. Do you guys have what number that is?
This is like the chapter number?
Yeah.
It's 1131.
And this one, 1131. This
No.
packet tracer.
This one is the packet tracer is 1129.
Yeah.
1129.
Yeah.
Okay, folks, note that one, please. Okay, let me keep going forward. Okay, configuring a basic router. So we have how we configure this device. Secure management access. So I want to really get this router configured to set this network up. So the old commands haven't changed. I mean, this is something familiar from our probably chapter 6, I think it is, in CCNA2. This is a line console configuration and a BTY 4 terminal lines being configured here. So routers and switches, I mean, the good thing about it is they have similar config steps. You name the device, you give it secure access, you configure the banner, and then you save it. Okay, that's not different from what we had before. So this sort of stuff should be commonly in your engineering journal. In fact, you already have configured a router before. You did it in your exam. Then configuring an interface, an IP version 4 interface. So here we've got a few extra commands here. This is, with routers, they support both high speed and gigabit Ethernet interfaces. The WIC I talked about earlier on, yeah, the EHWIC is a high speed WAN interface card. Sometimes when routers are a bit older or kind of like more convertible, you can put a gigabit Ethernet interface in there for high speed. So here we've got a configuration of an Ethernet, of a configuration of an interface. IP address mask no shutdown command. Just remember, in a lab environment, so in terms of the skill tests and so on, the serial interface with the cable end labeled DCE. If you ever come across that, DCE, and this is a hint because in skills test for chapter, this exam coming up here, there might be something like this in there. Yeah. So you need to also remember the clock rate command. That means that we have to make sure that both the clocks on the routers or devices have the same time. Even like millisecond, millisecond, millisecond. It's got to be synchronized. Otherwise, you can't get accurate timestamps and debugging, and it has other delays and issue complications. So clock rate is a key thing for configuration, also with router interfaces. Yeah, especially when you see the word DCE anywhere. Remember that, okay? If you ever see it coming up on a lab. All right. Configuring IP version 6. Now we did a bit of this. This was a bit of a scary thing in the exam, I think, as well. So configuring on, with the IP version 6 routers interfaces. Again, where you do it, you go to the interface you want to work on. So it's a serial 000 or an R1. We're configuring right here on this point. We're making a link to R2, giving it a version address, giving it its name, description. IPv6 address 2001 is the standardized name. DB8 a CAD31. It's been put on that particular port there. Clock rate, this is that DCE I talked about. A clock rate has also been provided, 1 to 8000. No shut. Okay, that's activated. So the command is IP version 6 address, as you can see here. Activate with no shut. It does say here, an interface can generate its own local link address without having a global unicast address by using the IPv6 enable interface config command. To say here, the clock rate was used as this is in a lab environment. Configuring the R1 interface continued. Okay. Just says an IP version 6 address must have a link local address, but will most likely also have an IP version 6 global unicast address. So you have two addresses active. These commands can be used to create these addresses, so whether they're global uni or local link. So you've got IPv6 address, and the difference is with link local is you put that link local word at the end, okay, to create that local link address. Loopback interfaces. So this is only a loopback. We call it loopback 0. In some situations, you will need to configure a loopback interface for testing and management purposes, it says here. The way we do this, the commands are interface space loopback space 0. Then you IP address it and exit. Now the loopback IP address specifically, you choose ones that are reserved. And there are some reserved addresses, particularly the 10.0.0.0 address. Yeah, that is a type of address which is reserved private. Yeah, you can see it's quite an odd address, 10.0.0.1. So if you see those sorts of addresses being used, that's normally how you would address loopback interfaces. It is a logical interface internal to the router, so it's not a physical interface, it's logical. That's what a loopback is. So therefore you can't connect it to any other device. It is a software interface that is automatically up as long as the router is functioning. Now some protocols require, okay, like OSPF is a type of protocol, requires an address for identification. And what you can do is you can use the loopback address rather than the interface address, which might go down on occasion, disrupting the routing. This loopback address is always up. Okay, so if configurations and so on happen, makes no difference. It's still a way of reaching that router. Packet tracer here, configuring IP4. Do you guys feel you want practice with IP version 6 as well? You still feel you need that practice? Yeah, that'd be useful. So I've therefore got this one out there as well. So I'm going to distribute this now. So this is something also I'll provide you. Let's take one of these each. 1, 2, 3. It's a config practice on routers, okay? It's got a practical thing. So I think when we come to lab time after break, I'll probably let you choose, but I would suggest going for We'll go through them all and just see which ones you want to start with. You know, you might prefer going with one of the easier ones like documentation, or you might want to go for actual hands-on config, which is good practice to remember how to do the commands. Asmret, can you take one pass it, please? Thank you. Right. So, folks, big chapter, still going through it. Lot to go. Oof, okay. So, verifying interface settings. The following commands verify the operation and config of an interface. These are the big ones to know about. So those of you who did your CCNA exam, hands-on skill test recently, that last page where it asks you for these little commands, look at these. Same ones. Show IP interface brief does that. Show IP route, display contents. Show running config interface ID, very specific command that. Show interfaces and show IP interface. Give you much more detailed information about what's going on in interface. Those commands are really hot and important, so please note them down, remember them, write them in your journal. IP version 6, exactly the same, except IP version 6 is the word before it. Okay? So we can just remember these commands too for doing the same things on those configurations.
Same command, but we just
IP.
pieces.
Pretty much the same, yeah. Okay. And you can see here, like this letter CLSU. C is a directly connected network. Yeah. L is a local network. So you can see that the ways that this is terminology used, it will help you understand how a network actually is constructed. Filter show command, this is a little useful thing. This little pipe character is really handy. You stick a pipe character on the end of any command, it does a search for that word. So I want to search all the IP routes specifically for the word begin and the word gateway. Yeah. So the word, these four here, I can do things like section line con, shows the section that starts with line con. So you can jump straight down the configuration file to the bit you want. Include down will show you all the stuff that matches down. Exclude up will exclude all of that. And begin line will show you all the line configurations. Just a really useful thing to have is that little pipe character. And now your CCNA2, you can use these advanced features. Command history feature. This shows you the previous commands. You only hit the up arrow. Yeah, the up arrow key will show you the last command you typed in. Control P will do the same thing. And it has a sort of size of how many commands it can remember. 10 is the command history on default. But I can make it much bigger. You can make it 200. Yeah. Also, you can go show history and it'll show you all the commands most recently typed. Good stuff. This is a package called Configuring and Verifying a Small Network. Okay, this one is pretty cool. Packet tracer activity. Let me explain to you what this one's about. You're going to configure a switch and a router, configure the PCs, verify connectivity. So, given the content of this, I would say configuring IP version 4 packet tracer and this one kind of go together. Yeah, like you practice on that one, and this should then be the next step. Like in terms of, you'll notice that when you read these things now, yeah, they're like a lot less detailed than the last CCNA1 was. Like they assume you know the stuff. Yeah. Okay, let's pass this out. Asmret, can you just distribute that, please? 5, yeah. Next one.
That will be the first one, and this is the second one.
No, the other one. Config.
Oh, this one.
Yeah, I think so. It'd be better. That's probably a better method, I think, to take with this. Sorry. Right now. Yeah. Everyone got one each? Great. Let's pile for those who aren't here today. Okay, move on. You've also got a lab here called Basic Router Settings. This is quite a long lab, and I think this is worth doing. It's quite a good lab to do. It's quite long. Maybe takes about an hour and a half, 2 hours to do it. But I would really strongly recommend to get strong router skills to do this lab yourself. Okay. And for this week we have only a chapter test exam for just this one chapter now. No heavy revision, so you can get back onto maybe doing the chapter test, obviously, and then doing a good lab. I really strongly recommend this one. Okay, on to routing decisions. I've got about 20 minutes to get through this rest of this. So, router switching function, encapsulating and de-encapsulating packets. Remember this diagram before? We had something like this before with 7 layers, and we de-encapsulate. We're going to chop off all this stuff when we forward things on. We don't need this stuff when it's going through the routers. Okay, we strip off that stuff. We go down to the data, the source address, the MAC address, the destination addresses. Then we get to here, and simply just IP address, all IP address stuff, some other fields and data, and it goes through. When it comes back here again, we then put back on the other layers and we de-encapsulate. Okay, so that's what's going on here when the layer's changing. The switching function encapsulates the packets in the appropriate link data link frame type for the outgoing interface. So a router is using a switching function. Okay, let me define again. A router uses a switching function, accepts a packet on one interface, and forwards it out the other interface. Okay, so it's not the same as a switch, by the way. It's just literally taking it from one interface to the other interface, and then the encapsulations are also taking place. When a router receives a packet from one network destined for another network, it performs 3 steps. 1. De-encapsulate the layer 2 frame header and trailer to expose the layer 3 packet. Step 2. Examine destination IP address of IP packet to find the best path. If it finds a path to destination, it encapsulates the layer 3 packet into a new layer 2 frame and forwards the frame out the exit interface. So the layer 3 IP addresses don't change as it moves router to router, okay? But the layer 2 data link addresses change at every hop as it's de-encapsulated and re-encapsulated. That's what's changing as you go through. It's a layer 2 data link address. Sending a packet, so this is a PC1 to PC2 across these 3 routers here. So here are the steps involved. We're just going to break this down in terms of step by step. So you watch what happens, okay? Look carefully at this. Maybe follow it on your screen with your little interactive version there. So PC1 must determine if the IP address for destination, it wants to go there, yeah, 4.10, is on the same network. It's on 1.10 itself, okay? So the problem is it's not on the same network right now. PC1 will obtain the destination MAC address from its ARP cache or use an ARP request. Because the destination network is on a different network, it goes, oh, hang on a minute, it's not on my network. Switch is not going to do much right now for me. I haven't even got a switch, so I'm going to go to my default gateway. That's my kind of last resort, yeah? So default gateway is the kind of router, and it forwards a packet there. So what it does is basically now looking for the default gateway address. You know, it uses the IP, it looks up on its ARP table, what is the IP address of default gateway, and the MAC address for that router, because it's all secure. We can get to our MAC address. Looks it up, does an ARP request if it's not found. And then once it gets the MAC address for that router, it forwards the packet on. Okay, so it goes to here. So now watch how this starts to change. This is the first stage. Here's the cache. Here's the MAC address. R1's MAC address. It's 0010. It's found it on the table. So then, once it gets to here, R1 examines the destination MAC address, which matches the MAC address of the receiving interface and copies the frame to its buffer. So between here and here, what's happening is it's going to need to move it from there to there. It's worked out it's an Ethernet type OX800. It de-encapsulates the Ethernet frame. Because the destination address of the packet 4.10 doesn't match any of the networks on R1, neither there nor there, it then starts to search its routing table for a route. So it looks up his routing table R1 and goes, right, do I have 4.0 on my list? It finds it right there. It has 2 hops, and it also now knows what is the interface to exit on, the egress, to get to that particular device. And also what is the IP address of the next hop IP. Just that information's enough to move it further, okay? Yeah, 2.2 is right there. So it knows to go there, and it's got some more hops after that. So a route was found. Gets to there. So R1's received it. See, this is repeated stuff. Yes, got to 2.2. Yes, just repeated actually. R2 forwards the packet to R3. So now here R2 examines the MAC address for destination. And so it's just repeating the same thing. Again, it has, I mean, this is all local information. R2 determines the frame, contains an IP packet in the data portion. It de-encapsulates it. It notices it's on a different network again. So it does a search on its routing table to find that .4. It's investigating it. It finds it has got a route. So 3 network has a route to 4 via a certain exit interface, which is serial. It's encapsulated again and sent out of the serial interface. It's got to R3 across the red line here. So R3 copies the frame into the buffer, de-encapsulates it, searches the table again for this next address. So it's very lengthy, this is quite slow, but it's just, this is how it's doing it to find the right interface to go out from. It's on 4, doesn't need to go to another router now, it's all on the same right network. It's on the exit interface. So what it does now is, because it's now on a directly connected network, R3 can resolve the IP address and get the MAC address from the cache. Yeah, because it's now on a secure environment, it's on a local network area here. You can look up an ARP cache and do an ARP request and get that MAC address and complete that delivery. Whew. So there's some decision processes done by this flowchart, which is quite useful, of what happens when. It's a good way of understanding it. And the idea of determination of where does it go, which is the best way to go and so on. So directly connected network, if the IP address belongs to a network, that's the destination IP address, that's directly connected, it obviously goes out of that interface. Yeah. If it's on a remote network, it goes to another router. If it's no route, it goes to the gateway of last resort, normally the default gateway. Okay, those are the 3 ways you can move along a network on routers. Onto the maths now, best path determination. So we got this idea of hop count versus bandwidth as a metric. So we got here this red line is the speed of the connection, and there's various hops between these routers here. This is a T1 connection, fast, yeah. That's a slow connection, R1, R3 there. So what it's got to do is work out what is the best way to get to the a network, and it uses metrics. So the metrics is the value of distance given to a network. There are various rules around it. So there's different types of protocols, right? So when you configure a router, you say, right, I want to configure it for RIP, OSPF, BIGRP. This is all CCNA2 stuff, where you learn about the protocols and what they're going to do. So what they're all about, they have different ways of calculating. RIP has a hop count, so how many steps, jumps does it take? OSPF, open shortest path first. Cisco's own based bandwidth, which is cumulative, it means it adds up as it goes along from source to destination. And eGRIP, enhanced interior gateway. Bandwidth, which is the speed of the connection. Delay, load and reliability. This is the best one, they seem to say. Really great, fast protocol to move things along. So some of the terminology there to be aware of in path determination. One is load balancing. Say you've got 2 paths, same metrics, exactly the same metrics. What the router does is it goes, so I can send down both these channels. It's a bit like this, yeah. Say you're a lorry trying to deliver something, yeah. I'm going to take random things out because it's been a very long presentation. Let's say I've got to deliver some milk down a road, yeah, to a particular house. And I've got so much, maybe 24 crates of it. This is a farm. I'm getting really animated now. And there's 2 paths to get there. So because there's 2 paths, what I can do is I can split 2 lorries, yeah, take half each, get there same time, not arrive exactly at the same time, yeah. So this load balancing is a similar way of managing this. You can forward packets using both paths equally. You split the load half and half, and it goes down those carriers. You see T1 here? That line, yellow packet, that's what's happening. Sending it to here, this is splitting it because it's got equal cost. So the table here has a single destination network but multiple exit interfaces. So that's what happens. The interfaces are all going to the same place. This is called equal cost load balancing. If you do it correctly, it can increase the network performance. It can be configured to use both dynamic and static routes. And it also supports unequal cost load balancing. You might want to send 3 down one line and 1 down another line, just make it unbalanced for some specific reason. Okay, load balancing. Admin distance is an important term. So this is a quite important factor actually. There's a question below that actually. So this is about trustworthiness. It's a word they use. And they use a terminology called admin distance. Admin distance means the higher this number, okay, yeah, the less trustworthy that connection is in terms of distance. If it's a lower number, it's literally right next to me. I can trust it. It's more trustworthy if it's nearer, yeah, than if it's say 55 hops across the planet. Yeah, you get that? So that's the idea of this idea of hops. So if you've got multiple protocols configured and statics, your routing table might have more than one route source for the same destination network. You might have many ways to get to the same place. So it's got to choose. And each protocol prefers a different path. So how does it know which path to choose? So what Cisco IOS does is it uses something called AD, admin distance, to determine the route. You see here, like connected is 0, static is 1, egrip is 5, BGP, which is the internet protocol, external BGP is 20, yeah. OSPF 110, RIP is 120. So you can see here, which is the most trustworthy route out of all those? What do you think it is?
OSPF.
What comes first, egrip or OSPF in the list?
OSPF.
Egrip. The egrip summary route comes first, then OSPF, but then egrip. But egrip is here and here. But external egrip comes later, but yeah, OSPF is midway in the table. So just egrip is more reliable. It has many more Cisco proprietary things and more controls on it. So talking about the routing table now. The routing table, I'll try and do this in 10 minutes, the last 10 slides. We've got directly connected and remote network routes. So this routing table has information on DCs and remote routes. This routing table is literally a data file in the RAM which stores information. It contains next hop associations for remote networks. Show IP route shows the routing table. There are some terminologies about it if you do run that command. L, C, S, D, and O. Notice D links to egrip. I don't know why, yeah, but they put D on it. Something to remember, because I get confused with C and D are confusing. Like C is connected, is what that means, like connected. D is dynamic, egrip. Yeah. And S static and O is OSPF. So just kind of get a feeling for remembering those terminologies when you see this routing table here. Here's an entry on a remote network, a routing table. This is how an entry looks. So you see D. So what's D? D is, which one? D stands for?
Dynamic.
Very good. Yeah, dynamic egrip. Good stuff, right? Okay, here's that. So it says egrip, root source, destination. So there's different commands there, so different colors. So how is it learned? Destination network, admin distance, trustworthy value. That admin AD is there. Okay. Then next is metric to reach the remote network. Next hop IP address via the next hop IP address. Amount of time since the network was discovered. And here's the interface to reach that network, to reach there via this. That's the way out. That's how a routing table looks. Okay, so this is just summarized by that. Directly connected interfaces. So here, a new router without any configured interfaces has an empty table. Nothing in it at all. This is one here example. There's nothing in there. It's empty. So before you actually make this interface up as in it's live, these are 3 things to remember, okay, when configuring a router to make sure that the green light is on. Assigned a valid IP version 4 or IP version 6 address. It's a good troubleshooting list here. Must be activated with a no shutdown command, and must receive a carrier signal from another device, router, switch, or host. Okay, when the interface is up, the network of that interface is added to the routing table as a directly connected route. DC routing table entries. So this is how it looks. So you've got the C and the L here. L is the local and C is the directly connected. Let's do commands.
So the L is local, it says?
L is local, yeah. Verifying, you can use those commands. There's examples are directly connected. So when it's configured, they're automatically added to this routing table as on the left. Show IP route, here they are. C and L are now on this list because they were put on a no shutdown to activate them. IP version 6 example, this shows you IPv6. Show IPv6 route will show you the routing table for the v6. C and L also apply to this as well. And you can ping to verify connectivity straight to a IP version 6 address there like that. You can ping IPv6 interfaces, yeah. Packet tracer, investigating directly connected routes. Do I have this one? Yeah, I have this one too. I'll give that to you in a second. This will let me show you how to probe into what routes are directly connected. It's probably something you can do secondary to the config exercises. Finally, static routes. So after you've configured a directly connected interface and added to the table, then you can configure the routing, static or dynamic. So first we configure the interfaces, then we configure the routing. Static routes manually configured and have a very specific path between 2 devices. They're both known IP addresses, start and end. If topology changes, so if you change something, you've got to do it manually, you've got to fix it manually. It's manually configured, manually reconfigured. Benefit, security, good, because you keep that address secret or whatever it is, yeah. And you can put more kind of controls on a fixed IP address. And it's resource efficient, no calculation needed with a static address. You kind of know where it's going. You don't have to work out a routing table path, do you? You just know it's going there. That's a convenient thing about static routes. And you've got to learn about both static and dynamic route configuration. Types of route, static. You've got static route to a specific network, and you've got a default static route. And the way you configure a static route is you do this command. IP space route, network mask, that's your address mask. Next hop IP address, that's where am I going to, and my exit interface. So it could be 192.168.3.0. You know, this is like a via serial 000, e.g. Yeah, that kind of thing could happen. So that's the way you're going to need to address this when you're filling out a command. Here's an example right here, right below it. This is a static route to like a printer or something, yeah, or a server, and it comes up as an S. The other option is, you've got default gateway. There's also a similar thing called a default static route. This is like, say a destination network is given and the router can't find it in the routing table. This is a fallback, yeah, like a default fallback for routes. So if you use the command IP route 00000, so like the destination is going to be 0, yeah, and this is called the quad 0 statement. So IP route quad 0 exit interface next hop IP will give a default static route for anything that's going to not hit the routing table. Examples, there's some examples here of static routes there. So you can see 00 via serial 00 going out this interface here and then exiting. That's a configuration. So it shows a static route being configured. This is chosen to be a gateway of last resort. So it has used quad zeros there. So it's the default route. There's a configuration. So here are 2 static route configurations from R2 to reach the 2 lands on R1. Questions? Which route was configured to use the exit interface? You see that? Which is using the exit interface? 225. Which one? The first or second one? S00. So what one of them is saying go out of here, yeah, this point, 10.0, let me find it. IP route 10.0, this is from R2 here to reach R1 lands. IP route 10.0, which is going to be there. So to get to that network, here's a mask, go out of S0000. So R2 is saying come out of this interface here. That's the interface configured to reach there. And 11.0 is saying use 200.225, which is 200.225 is over here. Yeah. So that one is using the exit interface. That one is not. That's over here instead. Will they send packets? Will they send packets for these networks to the same router? Will they all go to the same router? Yeah. They've all got to go here, haven't they?
Yeah.
So yes, they will all have to end up on R1 to handle. So that could go either way, to get there or get there. That's the configurations needed to reach these two LANs from that router. Okay. Some other examples. So IP version 6 is the same, but it's the same kind of style. Configuration, look at this, CAD 164. One of these routes using an exit interface, that one there. The other one uses a next hop, which is that one. Here's the configuration commands. You'll be able to do this practically when you do that activity, yeah, yourself, the config activity yourself. Best learned practically. Dynamic routing is a big subject, you know. I'm thinking just 2 slides, I'll just mention it briefly. So you've seen static routes there. Dynamic routing is basically done by protocols OSPF, EIGRP, and RIP. We don't manually configure them. Those protocols are configured, right? But they're more about, they've got sort of features to learn about other networks from other routers by automated way, by this idea of advertisements and routers just promoting, hi, I'm a router on the network. Everyone needs to know about me, kind of thing. So it says here, these networks and the best path to each are added to the routing table of a network because basically they're learned and they're added to the routing table. That's what's happening with this router. And this idea of convergence repeats there. They converged after they finished exchanging and updating their routing tables. Yeah. The router then maintains its network in its routing table itself. But there's an idea of having convergence at a certain point in time to do this. The types of dynamic protocols are as follows: EIGRP, OSPF, ISIS, RIP. You can use router ? To see the full list of what's available. There's a list put here. The dynamic protocols can adjust to change without involving an admin. They're kind of automated, and they also have a great advantage over static. Is that if there's a path, say with static, if it breaks a static path, the line goes. There's no backup. Yeah. But a dynamic protocol, if a static breaks or a path is unusable, it will find umpteen alternatives, ways to get places. That's really why dynamic is a superior routing protocol. Phew. Sorry, that's a beastly chapter, that one. Right, folks, just take some time out now.